So welcome everyone. Anyone who isn't here now will join us as we go along. Welcome to our virtual Zoom Science Cafe, the last one of the spring term before those of us at the university go into crazy examination mode. We've been online now for just about a year, and it's somehow, I think many of us at the university feel, in one sense, it feels as if we've been online forever, and in other senses, it feels as if we just blinked and a year has gone by. I hope it hasn't seemed like forever in all respects to any of you who are listening, but if we could add a little bit of human contact virtually to your COVID world, so be it. So Science Cafes, we've been running since 2008, so we're actually now um, quite well established. We've been online for a year, so we have that quite well established as well. And the goal of Science Cafe is to let the uh, the public who support Carleton in every sense, financial and sort of reputationally and with their participation, hear the amazing things that are going on in the Faculty of Science. My name's Pam Wolf. I've been hosting Science Cafe now for I think 5 years. I'm part of the faculty of in the Department of Chemistry and Environmental and Interdisciplinary Sciences. So Science Cafe allows us to bring our science out to the community. And while we really miss the in-person ability, online gives us an interesting opportunity to reach out to people that we couldn't otherwise reach out to. So for those of you who were here early, we were sort of having that casual conversation before we started of how do we manage to keep the best parts of our online world while going back to the parts we really miss about our live world. Today's talk is by Dr. Manuela Winkter. She's the Canada Research Professor in Physics at the Department, snow mold allergies and allergy medications. So my apologies, I'm less coherent even than usual. She is a Canada Research Professor in the Physics Department at Carleton University, and she studies the smallest building blocks of matter. Her main study area is the ATLAS experiment at CERN, the particle accelerator in Geneva, Switzerland. And in fact, she is speaking to us today from Geneva, Switzerland. So that's one of those advantages to having an online presence that we would not be able to have if we were relying solely on being present in person. She is the deputy spokesperson for the ATLAS experiment. She's now on her second spokesperson, to whom she is deputy spokesperson. She's also a fellow of the Royal Society of Canada, and she tells me that one of the best parts of having much of her Carleton work take place in Geneva, Switzerland, is that it is the best place for going running, which is something she enjoys doing in what little leisure time her various hats allow her. But today she's going to talk to us about her work on the ATLAS project at CERN. So Manuela, I will turn it over to you and your screen.
Thank you very much, Pam. First of all, I want to welcome you all to this presentation. And please forgive me for wearing a headset. Unfortunately, all of my colleagues around me and other offices are also on Zoom sessions with their own meetings right now. And so it gets to be a little bit noisy around here at CERN. So the first thing I'd like to do is share my screen, and hopefully that will work out all right. Here we go. All right, I hope that everyone can see my screen, which should show a picture of me.
My apologies. Well, Manuela is getting her screen sharing up and it is working. I did forget to say, if you have questions during the presentation, if you would type them into the Q&A when you think of them, that's great, but we'll address them in the order they came in at the end of the presentation. Apologies, Manuela, I forgot to say that as we were going.
Great. All right, there you go. Okay, everyone, hello. My name is Manuela Winkter, and this is what I looked like in the pre-COVID days, before I stopped cutting my hair. I am a professor at Carleton University in the Department of Physics. I'm an experimental particle physicist, and I'm, as Pam said, I'm the deputy spokesperson of the ATLAS collaboration at the CERN laboratory. So I would like to sort of go through in this process. I want to say a few words about what is the CERN laboratory and what is the ATLAS collaboration, and also then tell you a little bit about what it's like to be a particle physicist and what we do there. So CERN is really an international laboratory. It's right on the Swiss-French border, right near the town of Geneva in Switzerland. And it's really a paradigm for international cooperation. There are dozens of countries that participate in the CERN laboratory. And I certainly invite you to visit cern.ch if you want to know more about CERN. And at CERN, we study the nature of the universe. We try to figure out what the universe is made up of. And it's a central focus point for international scientists to just seek out answers to fundamental questions about our universe by using particle physics and pushing the limits of the technology to do so. The mission of CERN is to push forward the frontiers of knowledge. It's also has an important role as a developer of new technologies for accelerators and for detectors. And in particular, a lot of the technology that we use can be found now in hospitals. For example, if you go and do an MRI or all kinds of detector-related instrumentation. It also is a very fertile training ground for scientists and engineers of tomorrow, and in an international and really a leading edge environment. And it's a very important training ground for PhD students, as I'll show you in a few minutes. It's also a place where people come from different countries to be united and work together in a common goal. CERN today consists of 23 member states. It has about 2,500 staff members. And it has 13,000 scientific users. So these are people like myself and my colleagues at Carleton University. We are invited to go and participate in an experiment at CERN. It also is the world's most powerful system of particle accelerators. So talking about particle accelerators, let me show you a beautiful picture of the Geneva countryside. If you've ever been to Geneva, here's the Geneva airport right here. This is the beautiful Lake Geneva. And the French border is roughly around here. And so what you see in terms of these circles, these are colliders. So here, this triangle here is the CERN laboratory. And each of these circles that you see here is a different type of accelerators. And what happens at CERN is we take particles, we accelerate them. So every time they go into one of these circles, they go faster and faster and faster, and you have two counter-rotating series of protons that travel basically at the speed of light, at 99.9999991% of the speed of light. And this accelerator that is 27 kilometers long and 100 meters underground. And the protons then collide in an experiment, such as the ATLAS experiment. And then the ATLAS experiment looks at the collision products. So why do we want to do this? Well, we want to study how matter interacts with each other by doing these high energy collisions in a laboratory. And the reason why we want to do this is we want to study the early universe, really just a fraction of a second after the Big Bang. At that point in time, the Earth, that's not the Earth, the universe was very hot. So energy and mass were intimately related. And everybody knows, of course, Albert Einstein, and you probably know his equation. Well, his equation actually is very relevant to what we do. His equation says that if we have energy E, we can convert it to new matter. So this is what we try to do in this proton collisions. We take the protons, we collide them, we turn them into energy, and then this energy can be converted into new types of matter that haven't existed since the beginning of time. So really, the LHC is like studying the universe, less than a billionth of a second after the Big Bang. And the LHC actually stores quite a lot of energy. And just to relate to you what the energy is like, it's 360 megajoules. which is the kinetic energy equivalent of about 450 cars going at 100 kilometers an hour. It's the chemical energy of about 70 kilograms of chocolate, and it's enough thermal energy to make a ton of tea. Okay, so we want to take protons, we want to accelerate them and collide them. So first of all, where do we get our protons? Well, we go out there and we buy a bottle of hydrogen, because hydrogen, if you look at the hydrogen atom, is nothing more than a proton and an electron. So if you can strip the electron off, you're left with your proton, and you inject the proton inside the accelerator. There we go. So here I have my protons. Every time they go into a new circle, they go faster. A new accelerator, even faster. And then they go into the next one. So you see two bunches of protons there. And you can see they're now traveling in that ring. And then finally, they go into the Large Hadron Collider, the LHC. So let's go down underground into the LHC and see what happens if you were a proton going down this tunnel. So you see the tunnel here, which is the LHC, which is on the Swiss-French border. And from the inside, you can see a proton here with its constituents, because a proton is not a fundamental particle. It has other things inside. So you have protons coming in from one side, you have protons coming in from the other side, and then they collide right in the center of an experiment, such as ATLAS. And so all the things that you see coming out, all the lines, they all represent different particles that are coming out of this collision. So the final moment that you saw there is this collision point. So two protons coming in, and out comes all these particles. Another way to view it is here you have two particles coming in, they turn into energy, and from that energy turn into new matter. Now, it's great to make these collisions, but you know what? If you don't have some sort of camera to see what the collision products are, it's kind of useless. And so you need to have experiments that act as cameras. And these cameras have to be very performant. It's not just, you know, an iPhone that can work. It needs to take about 40 million pictures per second, every second, for about 9 months a year. So that's an awful lot of photographs of collisions. And that's why at the LHC, we have 4 such cameras, first 4 such experiments. And ATLAS is the one that myself and my colleagues at Carleton University work on. Here's a representation of ATLAS. If you were to go underground, here's for scale, you see this little person here. That's to give you an idea for the size of ATLAS. It's a detector. It's capable of identifying all the products that come out, the particles that come out of the collision. It lives about 80 meters underground. So the protons come in this way, and they come in this way. And this point here is about 80 meters underground. And this whole size here is about the size of a 7-story building. So it's really huge. And the total weight of the ATLAS experiment is about the same weight as the wrought iron in this lovely tower in Paris. So it's also very heavy detector. So the protons, as I mentioned, they come in this direction and in this direction. They meet in the center of the detector, and they collide. So the collision products come out from that, and this is what they look like to us. So you see a lot of features to this, but let me just give you a feeling for what happens in this collision. So here's at the center, here's where the collision happened. Every time you see a line, it's actually a particle that's come out of the collision. It's a particle with a charge, an electric charge. You see these different blocks. The different blocks represent how much energy the particles deposited in the detector when they went through it. So in this little square here, it's not an awful lot of energy, but in these big squares here, it means that this particle came and deposited a lot of energy in the detector. And the cones that you see here are actually physicists' interpretation of what's going on in there. This cone is telling us that all these lines here probably are related to each other. Maybe they come from a common origin. So we want to put a cone around them to sort of represent the fact that they are, we think, coming from a common object. And that's the kind of collision products that come out. And this is the kind of, this is called an event display. And this is what we see at the LHC. But ATLAS is much more than just a camera that takes a lot of pictures. ATLAS is actually a collaboration of more than 5,000 physicists, students, engineers, technicians. Actually, we're almost at 6,000 now. They come from 40 different countries. And in our experiment, just in the ATLAS experiment, we actually have about 1,200 PhD students. So 1,200 PhD students are training with us right now, learning about particle physics and earning their PhD degree and moving on into the world. Even though it's about 40 countries that participate in ATLAS, so these are the countries that have a university or a laboratory that's participating in ATLAS. But if you actually count the nationalities of everybody who is working at ATLAS, it's actually closer to 100 different countries. So it really is just this amazing mixture of people from around the world working together for a common reason. So what is it do we study with these particle collisions? You may want to know. Well, we study the 4 fundamental forces of nature. So right now, and wherever you are right now in your office or your living room, every force that you feel actually can be boiled down to one of 4 fundamental forces. The first one is gravitational. This is maybe the one that you're most familiar with, right? It's the one that keeps you in your seat right now. It's actually the one that we know the least about, surprisingly enough. Then there's the electromagnetic force. All right, if you've ever, played with magnets, you know about that kind of force. It's also related to electricity. Then there's something called the weak nuclear force, less well known in everyday experience, but however, absolutely essential. That is the force that is responsible for the nuclear burning in the sun. So without this weak force, we would have no sun burning. And the final fundamental force, which is again one that is maybe not as well known, but is absolutely essential to your everyday life. It's the strong force that keeps the constituents of your protons inside the proton. So like I said, your body is made from atoms, and inside the atoms, there's a nucleus, and inside the nucleus, there are protons and neutrons. And inside those protons and neutrons is other stuff called quarks and gluons. And that other stuff stays in there because of the strong nuclear force. So it's actually a very fundamental force and very important to your life. So those are the 4 types of forces that we study. And so what do we study about these forces? Well, these forces interact differently with different types of matter. So for example, if you have 2 electrons together and you bring them close together, they actually know that that each other is present, right? So they know this because they exchange information between each other. One electron says, "Hi, I'm an electron. I have an electric charge." And the other one says, "Me too, I have an electric charge." And so this is the electromagnetic force that is responsible for this. And the way that it's responsible for this is we can think of it as little carrier pigeons. Information or particles are actually exchanged between the electrons. So if it's the electromagnetic force, it's these photons that get exchanged. And if you're talking about some other force, for example, the weak force, then it's a Z boson that may be exchanged. Or if it's gravity, it's something we think is called, something we call gravitons. We're not 100% sure it's really exists because we haven't actually really detected them yet, but this is our hypothesis. And so these different forces act very differently. So let me just try to relate this to something that you would know. So if you take the sun and you take some very distant galaxy somewhere else, they actually feel each other. They know they can feel each other's gravitational, through the gravitational force. They feel each other's influence. And that's because we think that gravity can be felt infinitely far apart. Similarly, with the electromagnetic force, if you take an electron here and you take another electron, you take it on the other side of the galaxy, in principle, those 2 electrons can still feel each other's force. The other 2 forces actually only interact with very short distances. So the strong force, remember that's the force that keeps the constituents of your proton inside the proton, they only act basically a distance, which is the size of a proton. And the size of a proton is about 1/100th of a billionth of the width of a hair. So it's really very short distances. And the weak force related to nuclear burning, it's even 1,000 times shorter the distances. So that's what we study. We study how matter and the forces interact with each other. Here's a little diagram of how the universe progressed from the Big Bang all the way to today. Now, from our point of view, from the particle physics point of view, all the cool stuff in the universe happened in the first second after the Big Bang. Now, of course, other cool stuff happened after the first second, you know, for example, galaxies formed and planets and people, etc. But from a particle physics point of view, all the fun stuff happened in the first second. So in the first second, there were 4 fundamental forces, just like there are today. However, if you can go just a little bit before the first second, like the first billionth of a second, we know from the laboratory measurements that we've made that actually 2 of these forces, the weak and the electromagnetic forces, are actually just manifestations of one common force called the electroweak force. And this is the time, the place and time that the LHC has reached forces. This is where we study the phenomena of particle physics right around here. And it's very, very interesting to us because we have indirect indications that if you could go earlier in the universe, so even hotter than what the LHC could provide in its collisions, these 3 forces actually were 2 forces. And if you can go really, really early in time, 1 times 10 to the minus 43 seconds, then in fact, the 2 forces perhaps were just 1 fundamental forces. So as the universe cooled and expanded in the first second, you went from 1 fundamental forces to 2 to 3 to what we have today 4. And that's what we study. So once we have our collisions, what do we do with them? Well, there are 3 types of things that we do in terms of studying the physics behind it. The first thing we do, especially every time we take new data, we hurry out there and we try to search for new phenomena. So new things that we don't know about, new particles. And we have a lot of potential new particles to look for. There's a lot of theory out there that says, you know, if my theory is correct, then you should be able to see these new particles. And so we search for them. We search for them trying to get several bits of information about them. So let me relate this to, let's say you saw a really cool car on the road. It's just like, wow, it's really cool. And you want to go talk to your friend who's a car expert and you say, I saw a really cool car on the road and I don't know what it is. So your friend will say, well, tell me about this car. You could say, well, you know, it had 4 wheels. Okay, it's red. 4 doors. Ah, okay, 4 doors. That becomes interesting. Was it a hatchback or? Oh no, it was a hatchback or not. Did it have a little spoiler? And then you start talking about the different features, like what did the lights look like? You know, and eventually you get enough information about that car to say, oh yeah, I think I know what kind of car you're talking about. So that's exactly the same thing that we try to do when we search for these particles. We try to search for as much information about them so that if we were to discover it, we would be able to relate it to the theory that explained it. All right, so that's why we need to know as much as possible. And so in our diagrams like this one here, what you usually do is we say, okay, well, let's make a graph of one property of the particle versus the other property of the particle. And if we haven't seen this particle, we looked for it and we didn't find it, then we'll say something like, well, you know, we didn't see it. And if we didn't see it, doesn't mean it doesn't exist. It could mean that just that the LHC's collisions are not powerful enough, not strong enough, not energetic enough to produce this new particle. Maybe this new particle is so heavy that you just don't have enough energy to do it. So we plot something like this, which would be the mass of this particle, if we were to find it, versus some other property. And we could say, well, we looked up to here, we excluded everything in this range of the phase space of our particles, And maybe, you know, with more data, or maybe if the energy could be increased in the LHC, we could try to look for it in this region here, which is not yet excluded. So that was searching. Sometimes we get lucky, we search and we discover, and this is probably the coolest discovery in my career, and probably in the career of a lot of people in particle physics. We searched for a new particle, which is called the Higgs boson, and we found it. So here I'll show you a diagram of this Higgs boson. So this is the mass of this Higgs boson, or this new particle. And on this part here, it says basically how many of them we saw. So this blue peak here represents the Higgs boson. So before the LHC, we were not able to study this area here, and we were not able to see this Higgs boson. So in this particular case here, you can see that if you were to count up the numbers of particles here underneath this 15 here, you got 15 here, and maybe another 10 on either side, maybe another 5 on either side. You sort of add it all up, and you get that you have, you know, quite a good number of these particles, and you can really convince yourself that what you see really is something new. This red thing on the side here, which looks also very impressive, is something that we already knew about. So it's nice to see it, confirms that we know what we're doing, but it is something that we had already seen before. So if we find a new particle like we did with the Higgs boson, we write about it and we say, hey, we found this new particle and we measured its mass to be whatever the mass is of this new particle. Now, this particle was actually theorized already in the 1960s by 3 scientists. And when ATLAS and its sister experiment, CMS, it's another experiment, discovered the Higgs boson, the Nobel Prize was actually given to the 3, well, there were only 2 left at that time, the 2 theorists who predicted that this would happen. And this couldn't have happened unless ATLAS and CMS had discovered it. And this is often how we work in particle physics. We work hand in hand in the sense that theory will say, well, look, you know, I have this idea. Why don't you test it? And then the experiment will come along and say, well, I tested it and I don't see what you think you should be there. And then the theory says, okay, maybe, you know, try this other theory. And so back and forth, theory to theorize what to look for, experiment to either confirm that this is really there, or just as important to say, you know, that's not right. That's not what nature is giving us. And the third thing that we do at the LHC is to measure. We measure to great precision things that we know now not to great precision. All right, so we try to improve our knowledge of these particles. So we take a particle, for example, the W boson, which is you know, one of these little carrier pigeon messengers for the weak force. We knew about it. It was been discovered since the 1980s, but we try to measure it to great precision. And the reason why we try to measure it to great precision is that if we measure it to great precision, and we try then to compare to what the theory says should be the properties of this particle, if they disagree, if what I see is different than what theory says I should see, then either my experiment is wrong, that's always a real possibility, but the other possibility is that maybe there's some very subtle new phenomena that is not captured by the theory. And so that way you could actually discover new physics by measuring with incredible precision the things that you think you should know. So here's an example here of, as I said, this W boson. On this axis here, these are all the previous measurements of this property. This is the mass, and this line represents the uncertainty with which it was measured. So LEP is something that was kind of in the 1990s. It measured it with quite a large uncertainty. And then the Tevatron was a collider that was in the United States. It measured it to better precision, and then people sort of added those two together to get, you know, an even better precision number. And then recently, ATLAS measured it also to a comparable precision. And this is ATLAS's first measurement of this. We plan on doing several more. And here, this bar here represents the theoretical expectations for what this value should be. So you can see that those two here, in particular this one here, was actually a little bit different from the theoretical expectations, and people were wondering, is there a new science behind there? But the ATLAS measurement that recently was made confirms that it looks like this particle really behaves the way that we think it does. All right, I wanted to close this discussion by just explaining one big question to you. I mean, there are lots of big science questions that we try to do and understand at the LHC. So I thought I would try to explain to you one of the big questions that is very interesting to us. And I thought the best way to describe it is just imagine yourself outside with your dog and you want to play frisbee. All right, those of you who have a dog know that they're obsessed with frisbees. And also you may know that there are two types of these frisbees, these flying discs. There's the type that is solid everywhere. And there's the type that's just like a ring. The inside is empty and you throw it. Now, if you ever played around with these two types of frisbees, you'll know that the way you throw it is, if you want it to reach your dog, you're going to throw it differently. And the way it turns as you send it actually is quite different, right? Depending on whether you have a frisbee with a hole in it, or you have a frisbee that is solid in it. It's mostly solid in it. And so what I'm trying to say is how this mass, how this solidness of the flying disk is distributed along the flying disk dictates basically how it's going to move, its motion. All right, so now you're wondering, why am I talking about frisbees? I'm talking about frisbees because I want to relate this to our galaxies. So in 1959, the scientist here, Louise Volders, was looking at a galaxy, and this one here is the N33 Triangulum galaxy. And, if you look at the galaxy, it kind of looks like a frisbee, right? I mean, you have in this, you have, stars and planets and all kinds of things in there. And they're distributed in different ways. I mean, you can sort of see by your eye that there's quite a bit of stuff in the middle, and maybe as you go out, there's less of it. And so if you look at how all this mass is distributed in the galaxy, and you look at how it spins, she observed actually some very strange discrepancy. She observed that the galaxies were rotating in such a speed that the gravity that's generated by this matter could not possibly hold it together. All right, so here's a little graph of what it should. Well, here was the expectation. If you look at this galaxy, you look at all the mass and how it's distributed as a function of where you are from the center of the galaxy. It tells you what the velocity is. And so normal everyday physics experience tells us that, the velocity would be higher if you're closer. And as you go further and further away, the velocity goes down. But that's not what was observed. The observation was that, in fact, it seems to be quite flat. And that, fortunately, is what is keeping these galaxies together. Because if a galaxy were just following frisbee mechanics, this galaxy would have fallen apart a long time ago. So what is the possible explanation for something like this? Well, remember, it's all about where the mass is distributed in the galaxy. So maybe, just maybe, you just don't know where all the mass really is. Now, when we look at the galaxies, we always are looking at things that we call the luminous part, the things that we can see with our eyes and with our detectors and with our telescopes, etc. But maybe there's some other kind of matter in there that we can't see with our eyes. And so in the calculation that she made about how fast this galaxy should be turning, she only counted for the things she could see. She wasn't accounting for the things that she couldn't see. Now, by using the Hubble Space Telescope, astronomers estimate that there's some 100 billion galaxies in the universe. So if each one of them has some sort of missing mass in there, that's a lot of missing mass in the universe. And in fact, if you look at our universe right now, if you were to go out in the universe right now, you'd realize that the temperature of the universe is pretty constant. It's about 3 degrees above absolute zero. So if you look at the temperature of the universe, and here's a little map of looking at the temperature of the universe, you would realize that only about 30% of the universe is matter. And of that 30% of matter, actually only a tiny amount is the matter that makes up us, you, me, your puppy dogs, the galaxies and the stars. And in fact, you see in this breakdown here, only about, if you count it all up, only about this part here, so about 5% of the universe is made up of stuff that we know about. Then there's this other thing, which is 25% of the universe, which is the dark matter, which we think is the thing that Louise was taking into account when she was doing her calculations of how fast the galaxy should be moving. So this is the cold dark matter. And then the other 3/4 of the stuff is something called dark energy, which we have no clue really what it is. But at the LHC, we hope to be able to address at least this little wedge here, which is the cold dark matter. All right, how do we address this? Well, there's a very lovely theory out there called supersymmetry. It's a very elegant extension of what is our current best guess of how particles interact with matter. And if the supersymmetry theory were correct, not only would we see all the particles that we normally see in everyday life, but there should be a whole new other set of particles. In fact, a zoo of them. In this theory, in fact, every particle in the universe has, every type of particle in the universe has a supersymmetric counterpart. So it's a lot of new particles coming in. So what would we do with this? Well, how do we do this? How do we produce them at the LHC? Well, we take our protons from the LHC. Here's our 2 protons, and they collide. And in this collision would be creating, so here's the 2 protons colliding, making energy. And from that collision comes out these supersymmetric particles, if they exist. And in fact, what happens in these supersymmetric, so in these interactions that produce supersymmetric particles, what happens is you have this funky new supersymmetric particle, and then that decays into something else that's supersymmetric, plus something that is very common everyday stuff, which we can see in our detector, which let's call it Q. And then that SUSY particle travels a little bit further, and then it decays to another SUSY particle, plus something that we can see in our detector. And so on until you get to the end of the chain, and you get the lightest supersymmetric particle, which we think is actually stable. It means that if you produce it, it stays in the universe. And because these supersymmetric particles don't really interact well with our universe, we wouldn't be able to see them very well. And so these SUSY particles, right, could very well be the missing matter in the universe. So we hope at the LHC to actually create this missing matter in the universe, and try to detect it indirectly, and to convince ourselves that we know what this dark matter is. So far, we haven't seen it yet, so we don't know yet. Okay, this is my last slide. I just wanted to say a few words about ATLAS, what's in store for the future. So ATLAS, as I said, runs, normally 24 hours a day, 7 days a week, 9 months a year. But if you had a car that ran that way, every once in a while you have to stop and take it to the shop for repairs and to improve it. And that's exactly what we're doing right now at the LHC, is that for the past 2 years, we've stopped taking collisions to repair things, but also to install new equipment that's going to be more performant, because the LHC is going to keep on getting better at producing these collisions. So if we want to keep up, we actually need to have a better and more performant detector. And I wanted to show you in the end just a very short video, just because I want to show you some of the detectors that actually built at Carleton University. So Carleton has had this amazing endeavor in the last sort of 4 years or so, maybe a bit longer, at building some of this equipment for the LHC. And next month, in the middle of next month, I think the last component is supposed to be completed and shipped off to CERN, and that'll be the end of an amazing adventure at Carleton. And this construction has continued actually through COVID. Even though COVID has happened, we've still been able to continue to build this. And before I show you the video, I just wanted to let you know that Atlas is actually on the Google Street View. So if you want to take a walk inside the Atlas detector, you can find it on the Google Street View and see everything about it. So let me just show you, I'll just show you a little part of this video because it's a bit long, because I want to show you what was built at Carleton. And the focus is on these beautiful little petals that you see here. These are parts of a detector whose role is to identify muons. So muons are basically electrons, but the heavier cousins of electrons. And you can see here the size of the person here. This thing here is called a new small wheel. It's small because it's only 9 meters long, 9 meters wide. The big wheel in Atlas is actually more like a 25 meters in diameter. So let me just show you a few. I hope you can see this. All right, here's our muon, our new muon wheel. You can see one of these was being installed. Here's another one that's just being installed. And so inside this detector is actually what Carleton has built. And if you know the people here, which probably you don't, you would recognize some of our Canadian colleagues that are working on installing the new small wheel on the Atlas detector. Oops. So thank you very much for listening to me. I think I went a little bit over time, but I hope that you enjoyed it, and I'm more than happy to take on any questions.
Always worth going over time for particle physics. We have one question so far in the Q&A, so while other people organize their thought, if they have questions as well, I will relay that one on. Oops. Might as well be as friendly as possible. So the first question we have is, if we can't detect dark matter in reality, how can we detect it inside CERN?
Yes. So in fact, we detect it by not detecting it. So what we do is, so we know we have 2 protons coming in and they collide. And so all the particles that come out should go sort of uniformly in all directions. And so if we add up everything that we see, and we realize we have an imbalance, it looks like something went in one direction, but we can't see it. And that's how we would detect this dark matter. Its signature would be something that escaped the detector without being measured, and thereby violating, if you were to like sum up all the energy. There should be a conservation of energy. There should be conservation of momentum. And so if particles escape, we notice that.
So if I had a pool cue and the rack of billiard balls in their triangle, but I could somehow make the white ball invisible, I would know the white ball had to be there. I'd see my pool cue stop well short of that triangle.
Yeah.
A few minutes later, or a few seconds later, I would see the triangle go off in all directions, and I'd be able to say, wow, there's got to be a cue ball there, but I can't see it.
Yes, and in fact, it would be very challenging to play pool if you had these invisible particles and invisible balls, because you wouldn't be able to predict how the other ones are going to move because you're missing one.
Now, there's a thought. If I could color the cue ball the same color as the felt on the pool table, and I had to watch a screen that was photographing it instead of looking at the table, I could have a really interesting game of pool. But
Yes.
Of course, I'm terrible at pool even without. And since I know the physics behind it, I find that very frustrating that I should understand all of this and still not be able to get the ball in the pocket. So yes, very interesting. Another question by Catherine Dickinson. She said, did the theoretical physicists also visit CERN?
Yes, I didn't mention it because I'm not a theoretical physicist. I'm an experimental physicist. But CERN has the premier theoretical physics department in the universe, basically. So they have, just like in experiment, they do a training of early career scientists. They have programs where graduate students come. They also hire, CERN is very good at hiring people for short periods of time for training. So 2 years, 3, 4, 5 years, a sort of a stepping stone towards a permanent career. And yes, it's very vibrant. They actually have a very interesting series of talks, colloquia. They organize conferences, and it's great because we are able to interact with them in trying to understand our own science.
And a question by Simon Sunatori. There's a very recent news item, evidence emerges of brand new force of nature at CERN. What is this all about?
Brand new force of nature at CERN. I'm not aware of brand new force of nature at CERN. Certainly there have been announcements of something called a new particle called the autoron that was announced. It's fresh, it's brand new what's come out. Atlas hopes to also be able to look for it. I don't think that it's really confirmed entirely that this really exists yet. So it's certainly a very interesting indication. It's related to some of these fundamental. Remember, I talked about the strong force, and it exchanges particles. And the particle there is called the gluon. So the autoron is related to the gluon.
Does it have dark matter implications?
I don't think so. I don't think so.
Okay, I have a question of my own because I worked in that giant bay that was in the video in 1991 when the SNOW project was first being carried out. Yeah. So it brings back long back memories. But are the experiments? Yeah, I worked long before it was called Snow Lab. It was just plain old snow.
Yeah, that's right. Yeah.
And it's now Snow Lab. But I was going to ask, how do the Atlas investigations of dark matter complement or contrast the Snow Lab, which has dark matter projects? It isn't entirely that, but it has dark matter projects, yeah, and is here in Canada at Sudbury. So how are those two complementary or contrasting?
They're actually very complementary. A lot of the experiments in this laboratory called Snow Lab, which exists, it's just in Northern Ontario. It's not very far away. A lot of these experiments, what they do is they try to detect existing dark matter. So they often have these detectors that sort of wait and look for dark matter, are very sensitive. Maybe they say, okay, dark matter will pass by, and when it passes by, maybe it'll have a very subtle impact on our detector and we can measure it. Whereas the LHC takes a different approach, which is to create the dark matter. So in the collisions, we create dark matter that wasn't there an instant before. And so the physics reaches are very different because you can access very different types of dark matter. And it's really important actually to have these two different types of approaches because we don't know what dark matter is. We don't know yet what it's going to look like. And so you need to look at it from all directions. So one of the things that I love about dark matter and the explanation that I was giving about Louise Mulder's and the rotation of the universe is I know that dark matter exists. I know it's there. It's not like, oh, I wish it were there and I'll go look for it. I know it's there. The problem is I don't know what it's like. And if I don't know what it's like, I don't know how to look for it. And so you have to try, all directions, all possible ways, either direct or indirect, to be able to either create it and see it or see what already exists now.
Interesting. So perhaps the LHC could offer guidance to Snow Lab on how to look and what ranges to look in.
And vice versa, actually, as well. And so, in fact, when the LHC and Snow Lab look for similar dark matter, but from different angles, what happens is, in these plots that I showed, where we search for things, you'll see actually, this is what the LHC has looked for. This is what Snow Lab has looked for on the same plot. And you can see that they're excluding different regions in that plot. So they're very complementary, and indeed, one guides the other in terms of what to look for. And of course, theory comes in as well, and theory will look at this plot and say, okay, well, maybe it's not the thing that I thought you should be looking for, and vice versa. I mean, sometimes the other thing is that in experimental physics, sometimes we try to look for things with no prejudice, no theoretical prejudice as to what we're going to see. So we try to have these very broad searches for new physics. We just look at the collisions and compare it to what we expect to see, and see if there are any deviations without sort of having in mind, oh, I'm looking for that particle in particular. Really, you're just looking for new phenomena.
Because when you're looking for something, you can end up missing other things simply because
Yeah,
they're not what you expect to
yeah,
see.
exactly. And when you're looking for something in particular, you sometimes have these blinkers, like on horses, right? And you look very carefully at the thing you think you're looking for, and it could hit you from the side of the head without realizing it.
So you risk seeing things that aren't there if you really expect them, but even perhaps more of concern, you risk missing everything else because you just aren't looking with a wide enough range. Fascinating. That's it for the questions that we have in the Q&A. Does anyone have any more questions? And not seeing any pop up, I will thank all of our participants for coming. There's from René Dallaire and from Bob Burke, you have thank you that they enjoyed your presentation, that it was a great presentation. So
Thank
I
you.
will thank our speaker, Manuela Winkter, for taking time out of her day or her evening in Geneva to come to us. And thank our participants. As I mentioned, this is the last Science Cafe of the spring term. I don't know whether we have anything firmed up yet over the summer, but we were able to offer a summer session last year, and we will absolutely be starting again in the fall, whether or not we have summer sessions. I'm certainly hopeful that we will. So please keep an eye on the Science Cafe website for further announcements of upcoming seminars. And I hope everyone enjoys their spring, whether here or in Europe or elsewhere
Yeah,
around the world. And I hope to be talking to you again at a Science Cafe in the near future. So I hope Manuela can see the chat because it is exploding with thank yous and great presentations. So we
thank
will
you very much.
thank all of our participants and enjoy the rest of your day.
Thanks, everyone. Stay safe, and really look forward to having a Science Cafe in person, maybe in a year. Who knows?
Absolutely.
Thanks, everyone. Have a nice day.